So we have looked at solutions of equations, obviously. And then we look at general solutions. So when you think of a general solution of equation, and this goes all the way back to like linear equations. A solution of a linear equation is a point, xy, okay? But when you have a general solution, that's when you have like the function where you could plug in and get several functions or several solutions. When you think of it like an antiderivative, it's like when you put a plus c. It's general because we don't have definite to go by. And so we've done general solutions, we've done particular solutions, and we're going to do something called separation of variables here. And so the first thing we're going to look at is determine whether the given function is a solution of the differential equation, and then they give us y double prime minus y equals 0. So what are they asking? They're saying if I have a function, could I take the second derivative and subtract the original function and get 0? Meaning, does the second derivative equal the original function? That's all they're asking here pretty much when they ask. And so they're saying, are any of these solutions to that equation? Y double prime or second derivative of y minus y equals 0. So let's look at the first one. To find second derivative, you just take the derivative twice. That's pretty easy. So if I were to take the first derivative, the derivative sign is cosine. And then if I were to take the second derivative, right, then I would have the derivative of cosine is negative sine. And so they want to know what happens when I subtract second derivative minus original. Well, negative sine of x minus sine of x does not equal 0. That equals negative 2 sine of x. So that's not a solution. That's not a solution to that guy. Let's look at the next one. B. Y prime. Remember with this, we just do the original and then multiply by the derivative of the exponent. The derivative of this particular exponent is negative 1. So the first derivative is negative 4 e to the negative x. And then the second derivative does the same thing, multiplies by negative. So we get positive 4 e to the negative x. And this one, yes, I get second derivative minus original equation does equal 0. That is the solution. This is a solution to that particular question. All right. So then let's see if that works for any of these. Any of these. Well, the derivative of c e to the x is just simply my constant e to the x. My second derivative is my constant e to the x. So yeah, this is also going to be a solution. So really any log function like this with an x or even a negative x is going to work, all right? Any of our c to the x's there. Geometrically, the general solution of a first order differential equation represents a family of curves known as solution curves. One for each value assigned to the arbitrary constant. It says, for instance, you can verify that every function of the form y equals c over x is a solution of the differential equation x y prime plus y equals 0. And they have a proof for it as well. Talk about some terms here. Particular solutions are obtained from initial conditions, all right? So we've done something similar to this. I think we did it when we did like first derivatives and they told you the starting height and the starting velocity when we did, acceleration, velocity, and position. Initial conditions. So in order to have a particular solution, you have to know where you start. If you don't know where you start, you're going to have a general solution. All right. When they talk about solution curves, look at the picture there. So the reason it's called a solution curves, you can see why that term is there. Because depending on what your C is, if your C is 1, here we are, 2, here we are, negative 1, negative 2. So you can see that we have a set of curves that are created depending on what your C value is. That's a general solution. Your general solution produces an infinite supply of solutions is what it does. And so we go from a general solution to a particular by having specifics. And they used the position function here to even do it. So we have this position function. We don't know our initial velocity. We don't know our initial position. So then they give us an initial condition. Initial conditions will have a 0, that's your starting point. Or in a word problem, they will say it starts at the height, or it starts, the starting velocity is. And that's telling you a particular solution is what it's doing. S prime, that's your velocity. They told us the initial condition there, and you can back plug it. So if they told us our initial position here, they told us what this was. If they told us the initial position here, they told us what that was, and we get our particular solution. So that's all they're telling us. Nothing new. We're just going to use it going forward with separating variables. So let's look at example 2. It says for the differential equation x y prime minus 3y equals 0, verify that y equals cx cubed is a solution and find the particular solution determined by the initial condition y2 equals x when x equals negative 3. All right. So first of all, does cx cubed work? We're just going to first figure that out, and then we're going to go from there. And so in order to know if this works, we need to know what the derivative of that is. All right. And so we're going to take the derivative of this. Well, the derivative of this guy is going to be 3cx squared. Everybody agree with that? Whatever the constant is, we multiply by the exponent, subtract 1. So now we're just going to plug this guy into the original. So we have x times my y prime, 3cx squared, minus 3 times my original y, that's cx cubed. And we want to know, does that make that a true statement? Well, yeah, it does. X times x is x cubed. So we get 3x cubed minus, or 3cx cubed, 3cx cubed. Of course, that's going to equal 0. So that's we already know that works. So we're going to do that. Now it says, initial condition, y equals 2 when x equals negative 3. So if we know that this works, we're going to use our function to figure out what our constant is. In order to get a particular solution, we can't have a c in it. A c immediately tells you have a general solution. So we're going to do just like we did with our direct variation, like we did in the last section. We're going to plug these in. So when y is 2, so we're going to take that and plug it in for y. That equals c. What is x? X is negative 3 cubed. And then we just do solving, basic solving, right? Negative 27 times c, divide by that. C is going to equal negative 2/27, all right? Negative 2/27. And so now we have a particular solution here. To get the particular solution, we rewrite this guy. Our particular solution is y equals negative 2/27 x cubed. All right? Question. So this should work for this guy as well. If we plug it in, it should work because it worked in general. Consider a differential equation that can be written in this form. You have a function of x, a function of y, dy dx, and they equal 0. M is a continuous function of x, n is a continuous function of y. And we've done this before, separation of variables. Put all your x's with your dx, put all your y's with your dy's, and then you can integrate. This is called a separable equation, all right? And so they give us some examples. we have this little guy here, x squared plus 3y dy dx. We're going to move all our x's to one side and multiply by that dx. So it can be written like this. We would rewrite it that way. And then at this point, we could do an antiderivative. Sine of x, y prime. Well, y prime is just dy dx. So we would rewrite this dy dx, divide by our sine, multiply by our dx. Cosine over sine is cotangent. So you're just manipulating the function to get your x with your dx, your y with your dy, and then you're going to integrate from there. All right, that's all they're telling us to do. So let's look at this first one. Find the general solution of this guy right here. All right, so you want to put your x's on the side where you can multiply by the dx, and then you want to put your y's on the other side, wherever your dy dx may be. All right, in this case, I would have to multiply, I would have to move my dx over here, right? So I would have x squared plus 4 dy equals xy dx. I need my x's with my dx, I need my y's with my dy. All right, so I am going to divide this guy over, and then I'm going to also divide that y over, right? So on the left-hand side, I have 1 over y dy, and on the right-hand side, I have x over x squared plus 4 dx, right? That's how I would separate those variables. At this point, I can do my integration, all right? So at this point, I can integrate these. All right, we're going to integrate both sides. So we're going to integrate left and right. When I integrate 1 over a variable, what does that work out to? Natural log of y equals. All right, so over here, we could really do, well, we can do u substitution. So on the right-hand side, think of my u as my x squared plus 4, right? My du would be 2x dx. So I need an x. So it's just really going to be 1/2, right? So that's where we're going to get 1/2. And my u's on bottom, 1 over u. Well, that's also going to be natural log of x squared plus 4. You don't really have to do absolute value here. We really had to do it here because it has to be positive. But x squared plus 4 will always be positive, so you don't have to worry about absolute value. And then this is a general solution because we don't have boundaries, right? We don't have an upper and lower bound, so I do have to do this guy here, right? I don't have anything. This is not quite my answer because I need y. I need y equals something. I have natural log of y equals something. Anytime you have a general solution, think about when you had a linear equation. If you had negative y equals mx plus b, are you done? No, you don't have y by itself, right? And so I have to get rid of the natural log. So how do I have to get rid of the natural log by doing my e. So I am going to get rid of it by saying, I have e to this guy. So I am going to do e to both sides. All right. I'm going to do a couple things here, okay? A couple things. The first thing I'm going to do is I'm actually going to condense this piece of it, right? 1/2 in front can pop over to the exponent position, right? And so I'm going to move this in exponent position. Anything to the 1/2 power is square root, right? Yes? Yeah. And just like we did before, if I have a base like x to the 5, we'll say it that way. Well, that's x to the 2 plus 3, right? Everybody agree with that? So that is x to the 2 times x to the 3. Yes? So that's what I'm going to do here with this plus. All right? I'm going to make that e to the c times e to the square root natural log. We'll go from there. E to the natural log of x squared plus 4. Okay? Does everybody see what I did? We are. We're going to bump it. Right. Well, here we go. Here's 1/2. No, should be square root. Sorry, I've already taken care of the 1/2. E to the, there we go, square root of x squared plus 4. There we go. Everybody see what I did? So I moved the 1/2 into the exponent position, that's square root. And then I just said, well, that's c to this power times c to this power. or in this case, e to this power, whatever it is. My constant here being my c. Now, here's the thing. It doesn't matter. They have C1. You don't have to worry about C1, C2. It's just e to some constant. We don't know what that constant is, but we know that it's e to some constant. The other thing we did here when we did this is, let me move this up so you can see it. All right. This actually does take care of this, but I actually still have a natural log in absolute value. Over here, I do have e to some constant. These cancel out, right? And I have the square root of x squared plus 4. Is my y by itself?
No.
There is still an operation affecting my y. It is absolute value, which means my y could be the positive or the negative of that. So to get rid of that absolute value, I'm just going to say y is going to equal the positive or negative of that e to the c, square root of x squared plus 4. Everybody see what I did to simplify all of that? What is e to the c?
It's a constant.
It's just a constant, right? And so when you have e to some constant power, that in and of itself is a constant. So you can just say, well, that's really just y equals the positive or negative, but positive or negative is also just a constant, right? So it's just some constant, square root of x squared plus 4.
You can really just do that.
You can really just do that.
But if